I invite Dr. Sonia Balagovan to present her talk during this international conference. Please, Dr. Sonia.
Thank you. Thank you very much. That is a very, very flattering introduction. I'm sure I don't deserve any of it, but I will. Okay, so how much time do I have? I think I will start at 12 on the dot. And can everybody stay for 45 minutes, maybe? Hopefully, part of it at
Yeah.
least. Okay,
Yeah.
right. So I
Yes.
will start presenting. I can present here. And if I click on present, let's have a look at what the screen looks like. Um, I'm presenting my screen. I'm just testing out my screen. Um, I'm presenting. Okay, right. So maybe I just need to go back to that slide. Okay, can everybody see a title slide?
Yes, yes.
Okay, thank you very much. Okay, so I thought I'd talk about structure and symmetry, which is a topic I very cleverly took because I don't want. Anyway, first of all, thank you very much for your invitation. It's always nice to revisit Thrissur virtually, at least, and I can see my parents' living room on my mom's screen, so that's always nice. And I in turn welcome you all to Ireland and my kitchen. So. Um, but thanks very much. And let's talk about structure and symmetry, which is a topic I chose because I had no idea what I was going to talk about. So I thought I'd leave something very generic. Okay, so the area of mathematics I work in generally, it's called combinatorics. But what is combinatorics? Well, I mean, there is combinatorics, the human activity, which we do pretty much every day. If you're a child, you play around with blocks, which have different shapes and which have different colors and things like that, and then there's something in our brains that make us kind of go towards patterns and recognize patterns. That's just part of being human. That's combinatorial activity. You're going on a holiday somewhere, well, not right now, but in normal times, you go on a holiday somewhere and then you ask, oh, do I have enough shirts, do I have enough trousers, do I have enough skirts? And so you're kind of thinking about combining things together and putting them together, and this is a certain element of counting. You go to the shops, you hand over some change, and you want to know how you can make, say, 2.5 rupees out of various different kinds of coins. These are all combinatorial activities. We may recognize it as mathematical activity, but we are not sure if it's part of academic mathematics or not. I mean, to a great extent, I still am not. But what is combinatorics? When does combinatorics appear in mathematical form in the history of this human activity that we call mathematics? So usually pretty much every branch of mathematics evolves from the attempt to solve some problem. So somebody asks themselves or somebody else a question and people are trying to solve it. Some problems are interesting, some are not. And we have and you have questions. So initially, a lot of what we recognize these days as combinatorics came from India. Another source of mathematics historically has been Greek civilizations, but they didn't really care too much about counting. Like when they look at a triangle, they saw the properties of triangles, whether it's like a right triangle, whether it's an equilateral triangle, and what are the lengths and what are the relationships between various measurements. But if you're a combinatorialist, you kind of think of a triangle as a representation between objects and their and relations between them. But there's also another huge part of combinatorics, initially at least, was counting. So, and you see a lot of these counting problems in old texts, from including the Rhind papyrus, I think it's called, the very uh, old Alexandrian fragment, but also in ancient Indian texts. So a lot of early combinatorics came from texts like the Bhagavati Sutra, which is a Jain textbook, and also, but I couldn't find a primary source for it, so I picked a problem from the Sushruta Samhita. So what that is it's an old text of medicine, and it's an Ayurvedic medicine and surgery text, and it still survives to modern times, a lot of it, and it has been translated into English. So here on the right, you see an English translation of the Sushruta Samhita, where this chapter is basically one long calculation. So he wants to know how many combinations of tastes you can make. So there are these tastes: Madhura, which is sweetness; Lavana, which is saltiness; Amla, which is an acidic, sour taste; Tikta is is bitterness, kaduka is pungency, and kashaya is like an astringent taste. So if you speak any Sanskrit or you speak Indian languages, you probably know these words in some form or another. And he basically went and did the entire calculation by listing every single combination of tastes you can take, and he counted the answer as 63. As modern mathematicians, you would go, okay, there are 2 to the 6 possible combinations. Well, take away the one empty combination and you have 63. And funnily enough, this is an old combinatorial list trick. He put that computation into chapter 63. So this is something combinatorial. This is like our sense of humor right here. Okay, right. So also, if I'm speaking too fast, or if you have any questions or something, do drop a question in the chat box and I'll try and get to you when I can. Okay, right. Okay, so far, right. So that's combinatorics. And what about okay, so that's combinatorial stuff that appears in, and like a lot of Asian cultures did have a lot of combinatorial activity going on. They were parts of literature, or people were trying to do philosophy using this, and then it kind of arrived in Europe through various methods. So one of the great mathematicians of yore, Leibniz, who is also credited with the invention of calculus, when he started studying mathematics, for him he came through philosophy. So he wanted to mathematically prove the universality of human existence, and he wanted to prove the existence of God with logic. So I mean, these are probably activities that we no longer recognize as mathematics. But when he was talking about but he wrote a book called Dissertatio de Arte Combinatoria, and this is the first time in Latin or English that this is the origin of the word combinatorics. This is the first time this word combinatoria or combinatorial appears in the literature that we know of. Okay, so and he starts so he's doing some physics, metaphysics stuff I don't understand, but it does involve combinatorics in the sense of counting, and he has counting problems in it, and he talks about little identities involving binomial coefficients. Maybe they use different words, but that's what is going on. Okay, and then also, but he did get a lot of his ideas from the East. So he was in contact with Jesuit missionaries, and they sent him a copy of the I Ching, which is an ancient Chinese text, which is a book of divination. So again, this is, these days, in those days, everything was kind of, a lot of the stuff they did those days we don't recognize as science anymore, but that was their intellectual activity of the day. So he looked at this and he kind of realized, so if you can see this very faded picture, this is Leibniz's copy. And what he was doing was he's actually numbered these things. So here's a 1, a 2, a 3, and so on, because he basically looked at it and he goes, wait, these are numbers, these are the numbers from 1 up to 64. And so basically, if you have all broken lines, that's a 0. If you have an unbroken line, that's a 1. And every number from 1 to 64 can be written as a combination of zeros and ones in a and he basically just recognizes what we now call binary arithmetic, which is the foundation of all sorts of mathematics that makes the digital world possible. So we can thank the Chinese people who wrote this and Leibniz who recognized it for that. Okay, so and then to make it even more mathematical, so time passes and people are getting rich, and there are a lot of rich people with a lot of leisure, and they start amusing themselves with activities like gambling and questions about predicting the future and throwing dice and stuff like that. And this was probably the biggest driver of the development of combinatorics in the West. So Jacob Bernoulli writes a book called Ars Conjectandi, which is probably the first textbook on combinatorics and probability. And he does a lot of what we recognize now as combinatorial methods of counting various objects under various restrictions. And he thinks that that to learn to count things properly is a most eminently useful and worthy activity, which I completely agree with. Okay. So that was Bernoulli. He was working in probability, but at the same, and so that was mostly counting. But at the same time, there's another part of very integral to the activity of combinatorics, which is that of very discrete patterns. So here is one of my favorite works of art, and the expression on that, the a creator's face is just so relatable to me. This is exactly what I look like when I think about mathematics. And if you look very carefully at that picture, what you see is in the top corner there is if well done if you recognize that for yourself. That is a magic square. Okay, so a magic square, don't if you haven't seen one before, this is a very cool magic square where every row, every column, and the two main diagonals, and also the top, the four 2 by 2 squares at all the corners, and the middle 2 by 2 square, they all add up to the number 34. Okay, so this is a very, very cool magic square. And also he's using a little trick here where he does this engraving in the year 1514, and the 1514 is at the base of this magic square as well. So artists are looking at mathematical patterns, and magic squares are very old. The first known magic square appears in China, and they use math. So because there are these additive conditions that magic squares have to satisfy, they went off in the direction of thinking about simultaneous linear equations and things like that, which we all study a lot in school. Okay, now, so okay, so then we move on to Leonard Euler. So I know this is like a lot of about the history of mathematics, but the thing I realized was, a lot about the history of many branches of mathematics, but the history of combinatorics is something that I had to seek out and try and find out some stuff about. Anyway, so Leonard Euler, foremost mathematician of his time, maybe one of the top mathematicians of all time. So if anybody had to name the greatest mathematicians ever, Euler would definitely be one of them. So if Euler works on something and he tries to solve a problem and he can't quite solve it, that's immediately motivating to the entire world mathematical community, where they're like, oh, if Euler couldn't solve it, I should probably give this a try. Or, so he basically kickstarts branches of mathematics just by thinking about it and writing a note or two about it. So some of the things he's done is he worked on the 7 bridges of the Königsberg problem, which is a puzzle that people of the city were asking each other about, whether you could go through all the different islands of this city by passing all these bridges. And he proved that you couldn't by basically turning a real life situation into a graph, which is a set of objects together with their relations and so you connect to. So he noted various parts of the city by nodes, and then he connected them with a little line, with an edge, if you could uh, go from one to another. So that was basically, everybody says, okay, that's basically the beginning of graph theory. So people started studying these objects called graphs in their own rights and so on. Another thing he studied was geometry, and he wrote a paper called The Doctrine on Solids. And in there he has a proposition. So if you look at the last formula there, he's like, okay, if this is the number of corners, this is the number of edges, this is the number of faces, and if you put them together and they satisfy this formula. So all three-dimensional solids have that. But the Platonic solids were known to everybody, and even before then. But also, if you have, but he proved this more generally for other solid. He didn't prove it. He actually stated that there was a problem with this proof, but it was proved recently. Is everybody okay? Okay, right. So moving on, another thing he did was he actually wrote a lot about, he said, a paper on magic squares. They weren't about magic squares, but he considered the problem of the 36 officers. So what you have with the 36 officers, it was something somebody asked him. And so you have 36 officers, they come from 6 regiments, and in each regiment there's an officer of 6 different ranks. And he wants to know whether you can put them together in a way that nobody so you want to make them march in rows and columns, so that in no row are there 2 officers from the same regiment, and in no row are there 2 officers of the same rank. So, and that's a situation that we now call, that kind of arrangement is something we now call a Latin square. And Latin squares were also known way before Euler. I mean, Indian mathematicians knew them, and they used to know to work that they used Latin squares in order to create big magic squares and stuff like that. Anyway, so Euler looks at it, and then there were if you change that question a little bit to whether you could do the same thing uh, whether you could do the same thing. No, sorry. He said, okay. So he conjectures that this is not possible for 6 by 6, and then he also conjectures that you can't do this for any n by n, where n is some oddly even number, which is a number that's divisible by 2 but not divisible by 4. Okay, so in 1901, somebody actually wrote down all the possibilities, and by exhaustion proved that you can't actually do this. But also, but then later in 1959, two Indian mathematicians and an American mathematician, so that's Parker, Bose, and Srikhande, proved that it's actually, well, Euler was wrong. They're called Euler spoilers, that you do have magic squares, sorry, mutually orthogonal Latin squares in different dimensions, for different orders, different values of n, other than 6. Okay, so that's um, so okay, that was a problem that lay open for 250 years. I mean, and they finally solved it. Okay, so this is all combinatorial stuff. We would look at it and go, oh, that's a combinatorial problem. It's not exactly a counting problem. It's more of an existence problem of certain configurations. So that's, again, but we still don't have a branch of mathematics called combinatorics. It's not being taught. It's basically being used as a set of techniques for various other things, or as amusement. Okay. Okay, so I want to step forward another 80 years or so, and here is a copy of the Ladies and Gentlemen's Diary. So, and it says it's designed principally for the amusement and an instruction of students in mathematics, containing many useful and entertaining particulars. So this is like a little science magazine for students. So they come out once a year, and there are lots of problems. There's lots of like little write-ups that you can use, and people who are mostly homeschooling their children or tutors would look at this and kind of find things to do. This is the day before state-sponsored education and standard textbooks. So there was like a big kind of private sector of educational materials that people would choose and teach from. Okay, so in the Ladies and Gentlemen's Diary, if you look at the bottom right corner at the very end, there is a query number 6 by the Reverend Thomas Kirkman. So I've transcribed it over here. So he's the Reverend Thomas Kirkman from Croft near Warrington, and he wants to know, 15 young ladies in a school walk out 3 abreast for 7 days in succession, right? So you got 15 girls, and they're walking in 7 little rows, and there's 3 of them in every row, and you want to sorry, there are 5 rows in every little row. There are 3 people, and they go for walks every day, and they want to be arranged so that no two shall walk twice abreast. And this is called Kirkman's schoolgirl problem, and it became immensely popular. So every time in mathematics now, if you say Kirkman, people go, oh, the schoolgirl problem. And Kirkman absolutely at a stage came to hate that. He was like, I'm not just the guy who thinks about schoolgirls, I'm interested in other parts of mathematics too. And he was. So Kirkman was born in the English city of Bolton. He was the son of a cotton merchant. And when he finished school at 14, his tutor said, oh, you'll definitely get into Cambridge. You're great. And his dad said, no, we have a family business. Why would you go to college and waste your time? So come and work in the family business. Okay, so he worked in the family business for 9 years, and he was sick of it, and he defied his father, and he went to Ireland, unlike me, whose parents encouraged and paid for me to go to Ireland. But Kirkman had to run away from home and study in Trinity College Dublin, and then he came back and he became a rector in a church in Croft with Southworth. Okay, and then he married a woman, and he worked as a tutor for a little while. But also after a while, his wife inherited some property, so he didn't need to work. Being a rector was basically like being a newspaper columnist or something. He had to give like one sermon, and it didn't take any of his time. So he kind of went back to his love for mathematics, and he did a lot of mathematics. He discovered Hamiltonian graphs before Hamilton, and he knew Hamilton because Hamilton was based in Ireland, and he knew him from his days in Trinity. He discovered what we call Steiner triple systems before Steiner did. He worked a lot on group theory. He worked on hypercomplex numbers. He worked on polyhedral combinatorics. And at the right till his death, he was doing mathematics, and he published his paper on knot theory at 78. He was a very prolific mathematician, and he well deserves to be known for a lot more things other than a problem about schoolgirls. But he felt very isolated. He was living in a in a little village and he wasn't near anybody, and also he had some kind of fights with people, with Cayley and Sylvester. So Sylvester claimed credit for something Kirkman did, his solution to the Kirkman problem, and Kirkman said, "Well, I haven't even been to Cambridge, so what are you talking about?" So they all had these little arguments about who deserves credit for that, and but they're all dead, and we have the beautiful mathematics they invented, so maybe we shouldn't worry about that too much. So Sylvester and Cayley were also the same. They both went to Cambridge, but Sylvester never got a degree from Cambridge because back in those days you had to be a member of the Church of England, and Sylvester was Jewish. So basically he was awarded a degree by Trinity College Dublin, because they didn't care if you were Jewish or not. So he got his degree there, but he couldn't really find a position. He went to America, he came back, and he decided to change careers, become a lawyer. And Cayley as well, he went to college and he decided to be a lawyer. They both had difficulty finding academic positions in mathematics, which is very relatable right now. Okay, so they were working as lawyers, they met each other, and they started a 40-year collaboration where they talk to each other a lot, and they inspired each other to work on various parts of modern algebra. So they were also very great mathematicians, but they didn't quite get on with Sylvester, who thought that they were parts of the establishment and they were trying to keep him out. But it's a sad story. I would have thought they would have got on really if they were near each other. But sure. Anyway, okay. So these are various combinatorial things that were being done around the world, and then more and more people started getting more education, and people started thinking about things, and also various questions started coming up, not just mathematically, but also people were thinking about graph theory. There was the four color map conjecture, which drove a lot of development of graph theory. People started understanding chemistry in more detail at the molecular level. So they were looking at the structures of chemical compounds. People were thinking about partitions. So more kind of complicated counting problems. People were attacking them with things like generating functions, which came up because we knew enough analysis to work on things like generating functions, uh, and then people were doing statistics and communications and things like that. So various things like design theory, information theory, and all those came about as well. Okay, so that's how am I doing for time? I'm 20 minutes in, so another 25 minutes. Maybe I'll finish early. We'll see. Am I talking too fast? No?
No, it is
Yes?
fine, Sonia. It is fine.
Okay, thank you. All right. Okay, so that's early modern combinatorics. And if you want to know more about the history of combinatorics, you can uh, hold on. Yeah. Okay. There's this lovely book by Wilson and Watkins. It's called Combinatorics, Ancient and Modern, and they have a lot of essays collected about various parts of mathematics. So ancient combinatorics and how it developed in various parts of Asia, and about modern combinatorics, how it developed. So it's a good book. All right. At this stage, we're talking about the early 20th century, and combinatorics is pretty much a branch of mathematics now. People have inherently, so it shows up in mathematical problems. People have sort of hopefully accepted the mathematical nature of the combinatorial activity that we do. And here is Dorothy Maud Wrinch, who was a mathematician and a chemist, saying, for some reason which is not at present clear, the theory of the combinations of different sets of similar possibilities, which can be conveniently represented as the distribution of balls in boxes, is of utmost importance in many branches of science. So she was a chemist, so she would know. And she was also an associate of Russell, and she worked on logic and various areas like that. And this she wrote in a review of a book about combinatorics. So a book by McMahon, who was a combinatorist, and he was a contemporary of Ramanujan back in the day in Cambridge. So now people are writing about combinatorics as a branch of mathematics. There are books which are called things like combinatorial analysis and things like that. So it's about time people should start teaching it in colleges and schools and stuff, right? Okay. So and people are writing books, but we still haven't decided what combinatorics is, and it's actually a very hard subject to define. So I mean, basically it's up to you what you think, what you recognize as combinatorial and what you think combinatorics is. But here is Claude Burge, who was a very famous graph theorist, who thinks that combinatorics counts, enumerates. I don't know why he says that twice. I think counts is the same as enumerates, but French people, yeah? Okay, so combinatorics counts, enumerates, examines, and investigates the existence of configurations, which he earlier defines as uh, a configuration arises every time objects are distributed according to certain predetermined constraints. Anyway, so configurations with certain properties. And with combinatorics, one looks at their intrinsic properties and studies transformations of one configuration into another, as well as subconfigurations of a given configuration. I like that definition, but it's up to you. I mean, we still haven't agreed on what a good definition of combinatorics is. But as something that studies the intrinsic properties of configurations, and intrinsic as opposed to, say, for example, again, you look at a triangle, we don't care whether the triangle is embedded on a sphere or a hyperbolic space or uh, or what it is. We just know that a triangle is three things joined, where everything is joined to everything else, right? So that's intrinsic to the triangle, and extrinsic is all about sort of ambient spaces and things like that, which we don't generally care about in combinatorics, right? Okay, so I think we probably define combinatorics. Let's talk about a little bit more specific mathematics. So Kirkman's problem, people have found different solutions to it. There are 7 different solutions, and I won't tell you what different is, but they're in some sense essentially different. Okay, I leave that to you. We won't, if I wrote down some 7 sets of 3 by 5 matrices, it's not going to mean anything to you. But what about if we tried an easier problem, which is we make it a little bit smaller? So you can try Kirkman's problem, and if you write it down, you kind of find out that you will try a few things, and then suddenly you painted yourself into a corner. You'll have to backtrack and find more things. So it's actually a little bit harder. Okay, so maybe if you try something easier, if you have 9 young ladies in a school and they walk out 3 abreast for 4 days in successions, and it's required to arrange them daily so that no two shall walk twice abreast. Okay, right? If you can't solve a problem, try an easier one. So what about an even easier problem where you have 4 young ladies in a school and they walk out 2 by 2, and they do that for 3 days in succession, and we want to see if we can do that. Well, that's something that you could just get a piece of pen and paper and write, right? So you can just say, oh, okay, first and second, third and fourth, first and third, second and fourth, first and fourth, second and third, done, right? Okay, that's cool. And if you are used to doing mathematics, you know that if you have something like this, it's also kind of useful to draw pictures. I'm sure there are loads of graph theorists in the audience, so this is something that you would do, right? So what you've done is you've taken the complete graph on 4 vertices and split that into parallel classes. Right, okay, that's modern language, but back in the day we weren't thinking about that. Okay, what about the slightly harder problem then? So in the harder problem, you could do the same thing. You could go for day 1, you put them in a row, and then basically you can turn the rows into columns, and in day 2 you could have that. So you could write that out like this. So you could put them in a column like this, and then what you want 2 more days. So you could you could go with the diagonal AEI, and then B has to go with F has to go with G because it can't be on this row, or anywhere else, and C has to go with D has to go with H, and is it possible to do a 4th day? Well, let's see. C, then you have to send A and F and H together, B, D, and I together, C, G, and E together. Don't worry about it too much if you didn't follow that, but I'll give you a second to look at that, right? Does this remind you of something? If I put those girls together, and if it on the next day it was another day, does this remind you of Euler's-Latin squares? Maybe. Okay, right? So, well, anyway, so here it's a nice and pleasing pattern anyway to look at, right? So, sorry, should go the slide forward. Okay, so if that is the case, then you can write down there how we are going to send them out on a walking trip on days 3 and 4 as well. Okay, so that's Mr. Kirkman. Okay, so and then I leave the big question to you. Of course, it's left as an exercise, right? Another thing that makes combinatorics quite respectable is sometimes when you have a hard mathematical problem, at the core of it there is some combinatorial configuration you just can't break. Okay, so Julius Plucker was working on plane cubic curves in 1830s, and so that's like an equation. So y is equal to some cubic equation of x, and then he's looking at the space of solutions in some in some space, and then he is and then he so on the real plane, and then he looks at them and he realizes that a general plane cubic curve has 9 points of inflection. Don't worry about what that is, and they lie in threes on 12 lines. Moreover, given any 2 points at the system, exactly one of the lines passes through them. All right, and this is a configuration that we now know, and it's called the affine plane of order 3. Right, so here is a little flashback to the Kirkman problem. So Plucker was thinking about this. Plucker knew Sylvester. He told Sylvester about this, and Sylvester knew about this as well. Uh, Sorry, yeah, he probably told Woolhouse, who is the person who inspired Kirkman to think about the other problem. So maybe it all goes back to Plucker, and maybe Kirkman wasn't as originally thinking of this up himself either, because there were previous questions in the ladies and gentlemen's journal about these configurations and stuff like that. But anyway, here you have a picture, and according to me, I think that's a very pretty picture. So what we have here is points and lines. So when we talk about points and lines, we're not talking about straight lines. There is no concept of betweenness that we generally have in classical or Euclidean geometry, right? A line is just a set of points which are what we have instead of betweenness is incident. So they lie together. So it's just a set. If they're in the same set, they're incident. They're on a line. Okay, so here you have all these different parallel classes. So you got I should have colored that, but I kind of was lazy and I didn't. But anyway, it's a nice picture. You can look at it and you can see how the various points and lines are parallel or intersecting, and there are 12 of them and so on. And that's exactly the same one that we saw previously with the 9 schoolgirls. Right, okay. More algebraic geometry. People are discovering irreducible configurations that they simply cannot get around. So this one is Kummer was studying a quartic surface, and it's a I don't understand geometry really. So, I mean, this is Greek to me. So he has projective three-dimensional space. Okay, I kind of think I know what that is, but what's a node? Anyway, so so he studies some very complicated geometric object. If you want, you can look up Kummer's surface um, on Google, and you see kind of pictures that will melt your brain. Anyway, so this is all in higher dimension, projective three-dimensional space, and so you have these complicated things, but you have but the configuration of these nodes and these conics, nodes and conics, the way they intersect, it's actually quite easy to write down. So somebody in 1981, I think it was, I don't remember the name of the author. Somebody found this. So what you do is you take your 16 points, which are your 16 conics if you want, or your 16 nodes. It doesn't matter. They're interchangeable. So you want lines, you want blocks, right? You want six. You want to take sets of size 6. You want to collect subsets of the set for all numbers from A, B, C, D, E, F, G, H, L, M, N, O, P. So that's your 16 symbols. You want to collect them into sets of 6 each, right? So I just put them in any order. It doesn't matter. You just have to put them all in a block. Sorry, you want to put them all in a 4x4 grid, and what you do is you want 16 blocks. So how do you pick your 16 blocks? You take any one of these blocks. So here I've chosen N to be highlighted, and then you take all the other points. Don't take N, but take all the other points that are in the same row and in the same column as N. So you have COHLME. So you have, for each of these 16 squares, you can pick that, and you can take all of the ones that are on the same row or on the same column with it, and you get 16 blocks. So you got 16 points and 16 blocks. Each block is in 6 different sorry, each block contains 6 different points, because there's 3 on the same row and 3 more on the same column, and each point is in 6 blocks, because there are 3. It will be in the block of the 3 on the same row and 3 of the same column, and any 2 blocks will intersect in 2 points, and any 2 points will be in exactly 2 blocks. So it's a very symmetrical uh, system. So what you have there is what you call a symmetric design. There's other things also that come from algebraic geometry. So Gino Fano was trying to study projective geometry purely in an axiomatic way, and he came up with something called the 7-point projective plane, which is also known as the Fano plane. It came to have its name, but again, Kirkman had discovered the triple system, the incident structure. So basically, not the picture as such, but if you actually gave them all names, and if you took everything that was connected by a line into a block, so you get 7 different lines, so you get 7 different blocks of 3 made out of 7 points, and every point has 7 blocks, and any 2 intersect in exactly 1. You get that system. That Kirkman had discovered that before him as well. So, and again, he didn't get any credit. Poor Kirkman. Okay, so this is what we call a finite projective plane. So it satisfies all it's a finite set, which satisfies all the axioms of projective geometry, which is not something that you think of as a finite thing. It's you generally think of projective geometry as an infinite thing, but it depends on what field you're doing it over, and in this case, you're doing it on a finite field. But if you just write down those axioms for a set of points, you have a finite projective plane. Okay, so here, and then somebody clever came up with an easy way of remembering this, which is you just take the letters. If you read out the sentence, yeah, why try her raw wet hat, which is a weird sentence, but if you look at it, there are 7 letters that go into it. Every letter is in exactly 3 words, and any 2 words will have exactly 1 word in common. So that's an English sentence. That's a finite projective plane. I mean, that's kind of cool. Right, so there's all these combinatorial designs being done, and then also, so statisticians were thinking about it because they wanted to like not waste too many resources when they were doing their statistical experiments. So they wanted some nice configurations where you could apply treatments selectively, so that different combinations of treatments would be applied to different patients or different agricultural lands and stuff like that. So that's so statisticians were thinking about these things, and they came across these same configurations, and they called them block designs. Okay, so I call them block designs because I'm a graduate of the Indian Statistical Institute, where people like Bose and Rai Chaudhary and people like that like Bose did a lot of work on designs. So they called it designs. My professors called them designs, so I call them designs as well. Okay, and nowadays most people call them designs. So it's a part of applied statistics almost now, but it's also part of mathematics. So by this stage, um, combinatorics is very purely mathematical. It shows up in all these geometric situations, but it is also uh, it's also very applied. So people are now using them for tournament scheduling or scheduling classes, for lotteries, for chemistry, for biology, for design and analysis of algorithms, for networking testing. So if you want to do testing on groups of subjects, cryptography, it's everywhere, right? Designs are extremely useful things now. So, okay, we said what designs are, kind of. I glossed over the definition, but you can always look it up, or I can send you the slides later. There's a question of, okay, right, so you define these things, but do they exist? Yes, so a mathematician at Oxford called Peter Kiefish recently said that for all feasible parameters. So you can't have like designs with any number of numbers. They have to divide into each other evenly and so on. Right, so the number of blocks will have to separate out everything, and you don't have a remainder left over or something like that. So you can't separate 10 objects into blocks of size 4 because you'll have 2 left over. So that's so there are some parameters are feasible. There are some very very basic conditions for that, and for that and for and with very small exceptions, with small numbers you may not always be able to do it. But if so, here I call them tvk lambda designs, right? So for any k and lambda, if v is big enough, the total number of points is big enough, you could make a design, right? So that was solved using probabilistic combinatorics. That's another area of combinatorics altogether. And so he used probabilistic methods, and he found that you basically always have designs. Okay, right. That's a result that makes most people very happy, and I absolutely think it's amazing. But for me, designs are all about symmetry, and most designs don't have any symmetries at all. So what I am interested in is algebraic combinatorics of designs. So designs that are symmetrical. So if we go back, maybe if you remember back to the slides that we saw earlier, all those designs are quite symmetric in nature, right? I mean, this way you kind of twist them around, you can pick them up with your hands, and you can kind of move them around. They still look the same. There are, I mean, whatever you personally recognize or in your subconsciously recognize the symmetry, it is there. You look at them and they make you just that little bit happier, I hope. Anyway, so they are symmetrical, right? And but the best way of studying the symmetries of these things is through algebraic combinatorics. So again, all these, so as Krishnanandhan said earlier, it's not true that like there are no branches of mathematics. Everything is mathematics, and if even if you kind of put them into different bins, they're always helping each other and kind of providing ideas from one to another, and it's all rather I mean they kind of exist in a certain synergy. So if so basically you have linear algebraic methods, you have what you call them, you have matrices, and you using matrices you could do things like look at the spectrum of a matrix, and you could use that to write down the adjacency matrix of a graph, and you can use that to write the graph spectrum. You could look um, at linear spaces over finite fields, and you could do the linear algebra on that, and you get coding theory. So there are all these methods from linear algebra that we use in combinatorics all the time. Also, you have algebraic and number theoretic invariance, where you have like things like what's it called, polynomials, about graph coloring polynomials, not polynomials, things like that, and you use that in order to see whether combinatorial structures exist or not, because you check whether the invariants are satisfied. You have commutative algebraic methods, which have been used very to great effect to study combinatorial structures by people like Richard Stanley. And my favorite bit, which is when you use permutation groups, right, to permutation groups to study structure preserving symmetries. Now, what's that? So basically, say you have something like a design, you have all the points on the design, and then you look at the symmetry group, which I hope everybody knows what that is. If you've done some group theory, it's basically all the ways you can swap them around with each other. And then you look at the symmetric groups that also preserve the blocks. Okay, so I don't want to write that down. I'm sure everybody's just had lunch and you're probably already asleep. So let's not do any calculations in this talk. Anyway, so you look at structure preserving symmetries, which are quite beautiful, and then there's also other bits of algebraic combinatorics, like things like studying Young's tableaus, association schemes, metroids, which are all generalizations of algebraic concepts like linear independence and so on. So this is Josephine Yu. She studies combinatorics, and she works in metroids, and she says combinatorics is the art and science of distilling a complex mathematical structure into simple attributes and developing from this a deeper understanding of the original structure. So studying, for example, invariants, studying, for example, there was something on my, I forgot. Anyway, so you get like Birch said, right? If you look at the intrinsic properties, so you study the graphs based on that. You take a real life situation and you turn it into a graph, and then you look at the properties of the graph and use that to understand the real life situation, like who's friends with whom on Facebook and stuff like that. Right. Okay. So that's I think that's a very nice description of combinatorics. Right. So I have about 4 minutes, and I thought I should give you a very quick introduction on what I do as a mathematician. So I work somewhere between combinatorics and geometry. I can do combinatorics. Can do geometry with great difficulty. So what I do is, so you look at a space like a circle, and I don't quite like the fact that a circle is given by an equation x squared plus y squared equals r squared. So that's and also nowadays you have computers, so uh, computers don't understand anything x squared plus y squared plus r squared. But if you take a computer and you tell them it is the area bounded by 3 points and all the points are connected to each other, you could kind of replace things like equations with a set system. So that's what I study, and that was how algebraic topology came about initially as well. Anyway, so I study things called simplicial complexes, and simplicial complexes are models for sort of higher for manifolds. So, for example, if you take a sphere and you could kind of put triangles on it and you join them up in a nice way, and you get nice triangles, right? So I study spaces like projective space, where you translate the combinatorial conditions into geometric restrictions, and then I wanted to see, oh, what's the smallest you can make. So I don't know if you can see my feed. Here is a tetrahedron. For me, this is like the smallest model you can make of a sphere, by where everything is like flat and bounded by lines, and the lines are all glued together nicely. So okay, but if I want to make a projective space, for example, what I will do, I can't a project okay what I will do is I will think about, okay, what's a projective plane? It's the antipodal quotient of the sphere. what does that mean? I take a sphere and I take any point and I take the point directly opposite it through the center, and then I kind of glue them together. So here is the times where, like, this is not something that exists in three dimensions. You can't really draw a picture, but what you can do is you could say, okay, I take a flat disk and I take the boundary of that disk and I pick it up and I kind of twist it and glue it back together like this. That's a projected plane, right? If you can't see it, don't worry about it. I can't see it in my mind either. Okay, so for example, so if I want to say, okay, so instead of like a continuous smooth projective plane, I want to write it in terms of little flat triangles that can be glued together nicely and described in terms of finite sets, I have like a picture like this. So, and this will give you, so basically if I write down all the blocks, so this is now coming back to the language of design theory, this is now a set of 6 points and every triangle is a block of size 3. And any two blocks intersect in, sorry, any block has 3 points, any point is in 5 blocks, and any block, and yeah, any two blocks intersect in either 3 or sorry in 2, which is an edge, or 1, which is 0 point. So this is an isometric structure, and this is and you in and if you, and every time you swap around the 1 2 3 5 and 6, you get different different what do you call them, uh, you get different labelings of the same space, and this has and it has 720, no, sorry, 120 structure preserving symmetries. Okay, so that's symmetry makes me happy, so now I'm quite happy to do that, to look at that. Sorry. Oh, I want to, okay, and that is also when I said it's an antipodal quotient of a sphere. So here's my favorite icosahedron, and this is a platonic solid. We saw a picture of it before, and this, if you kind of quotient out by the antipodal map, as we say, or if you kind of flatten it by kind of mentally joining everything to its opposite point, that's the thing. Okay, right, I'm out of time, so I'm going to very quickly run through my next slide. So we do this in higher dimensions, and you find all these you basically, like, it's kind of very cool what happened in the case of uh, all of us working in projective space, which is that Frank Lutz is a German mathematician, and he kind of used a geometric idea where he started off with a big triangulation of projective space. You use computer searches, so you kind of just mess around with it and you break all its symmetries, but you just keep trying and make it smaller and smaller, and he found a space which has actually 720 symmetries, even though you have no symmetries as you go along. Suddenly when you come up to the minimal object, you kind of suddenly find a symmetry, right? So sorry, okay, and what I like to do is I like to use kind of nice symmetric objects that we already know, like groups and designs and things like that, and I want to kind of say, okay, right, now if that is the basic configuration inside of it, how do I kind of extend that out and make it into a geometric object? Like, what should I pick so that all these various conditions are satisfied? The combinatorial symmetry and also the geometric structure are satisfied. So you kind of so whatever Lutz found by computer search, I found with symmetries, and it's well, basically I took this object and I worked back from it, and I was like, oh, these are the symmetries, so now I know exactly what the thing does. Okay, so you kind of work on that. And then suddenly I was looking at the object a little bit more, because you never actually stop thinking about any of your problems, even if you think you solved them. I was like, oh, wait. So this is the geometry, and this is how it works. And then I'm like, but this thing is a lot more symmetric than I thought. This is actually contain, and I was able to establish connections of that with various other geometric objects that are well known. So here is a picture of the outer automorphism of Sim6. Let's not worry about that, and I'm 2 minutes over time. And here is a picture from my paper on the projective space. And this is like a nice template. You could look at it and write down the combinatorial object known as the nicest biplane. And if you kind of think about it a little bit more, you come up with something called the with design on 22 points, which is kind of quite famous in mathematics. Right, okay, so that's this quote kind of spoke to me. One starts out in life trying to do mathematics and winds up doing combinatorics. Okay, right. So like to do combinatorics, when I was an undergraduate, my professors would be like, combinatorics is hard. And I would say, well, that's what makes it fun. Okay. Well, so all the quotes I used on this page, they were all collected quotes on combinatorics by Igor Pak. So that's the link. If you want the slides later, you can click through there. And I want to leave you with a thought by the analyst Leonard Carlson, who solved very, very hard and difficult and important problems in Fourier series, where he says that every hard problem in mathematics has something to do with combinatorics. So I hope that has made you interested in combinatorics to some extent. And here are some books if you want to get started on sort of the kind of combinatorics that explore structures and symmetries. Okay, right. Well, and also there's a lot of combinatorics and symmetry in nature. This is the Giant's Causeway from Ireland. And thank you, and everybody stay safe. Hopefully we will all meet again soon in real life. Thank you.
Okay. Thank you,
I want to
Sonia.
stop presenting. Stop. Okay,
Okay.
thank you. Thank you, Krishna sir.
Yeah, okay. Anybody wants to ask any questions? Somebody will be having doubts. Can somebody ask why, how she was attracted to combinatorics? How you came to